Greetings, I'm Kevin, and you're watching Quantum Prophet. Today I'm going to be talking about quantum physics, a fascinating subject that, although it can be kind of difficult to understand sometimes, I'm going to try to make it as simple as possible to get the gist of it. And the reason I think it's important to learn is because I have a theory, or I guess a saying you could say, that everything is alive, everything is connected. And at a quantum level, those sayings aren't just sayings or cliches. There really is some truth to that. Now, a little disclaimer, as with most of these type of topics, there are hardcore materialists and the scientists, some scientists who are very rigorous or dogmatic in their ways, who absolutely can't stand when spiritual people talk about quantum physics because they think it's hijacking the concept. But I do think there are some things that are very interesting about it that, while they may not justify some of the spiritual beliefs, I think that there are correlations that are interesting enough that it's definitely worth talking about. And it's also worth noting that the Dalai Lama is very interested in quantum physics, in fact so much that he often holds conferences where he invites quantum physicists to come and speak with him because there are direct tie-ins to some of the consequences of the way quantum physics works and what Buddhist beliefs are. So I'll try to see if I can put a link or two below after this and see if I can link up some of those articles or talks with the Dalai Lama and quantum physicists, because they're really interesting. So for me, how did I find out about this or get started? Back in about 2005, I think it was, there was a movie that came out called What the Bleep Do We Know? And it starred Marlee Matlin. And I guess the basic subject matter of the movie is that Marlee Matlin plays a woman who's kind of, I guess you could say, a little bit frustrated, a little bit lost, and it's kind of hard to explain, but basically the movie goes on to include some actual people. It's kind of like a quasi-documentary, quasi-movie, and it introduces some concepts from quantum physics that kind of opened her mind and opened her experience and changed her perception. Well, after I watched the movie, me being the skeptical, I know some people might find that surprising, but I am actually pretty skeptical, and I do have a scientific mind. So after watching the movie, I thought to myself, this just sounds like too hokey, like that this stuff can't be true. That can't really be what quantum physics is about. So I set out on a quest and started buying books on quantum physics and studying everything. And it turns out that a lot of the stuff they talk about in that movie really is true at a quantum level. Now, what correlations you can make or what you think that means, that's up for interpretation as far as an individual. But I like to look at it from the standpoint of, because I believe in science and scientists, but the way that things operate in science and the way that things happen, I think we can draw our own inferences from them on things that aren't proven yet or things that they don't know how they work. In other words, it's kind of like the Big Bang. No scientist knows really what happened before the Big Bang. They have a lot of ideas, and they like to talk about those, but nobody can prove it. So it's just as logical in my mind to posit that there's some higher intelligence or creator that created the universe as it is to think that it came from a quantum fluctuation or there's a multiple infinite number of universes. In any case, the point is that I think it's good to just keep an open mind. So with that being said, let's talk a little bit about quantum physics. Quantum physics is basically the study of the most elementary particles or elementary constituents of matter. So we're talking about atoms, molecules, and even the particles that make those up. It turns out that the laws of gravity and the Newtonian laws of physics, the laws of motion and stuff, work great when talking about big stuff, but when you get down to the level of particles like electrons and photons, single particles, things kind of get weird. One of the first examples that a lot of people hear about or that's fundamental to quantum physics is wave-particle duality. So what this basically postulates is that the smallest particles of matter, like I said, electrons, protons, photons, exist in what they call a superposition, which is a state where they're both a wave and a particle at the same time. So this is kind of hard to wrap your head around, and so I'm going to put up some visualizations here to help us talk through them, and I'm going to look through them here so we can go through them together. So there's this experiment they did called the double-slit experiment. And this experiment is basically, they took you can call it like a photon or electron gun, and they shot single electrons through a piece of metal. I think it was a sheet of metal that had two slits on it, like in the image that I'm showing now. So the assumption would be that if you took, such an apparatus and shot an electron through one or two of the slits, that it would form a pattern like it shows there with a little, text is saying that if the particles behave classically, the pattern should produce the patterns on the back like two stripes, because they would go through and show in those little areas. What they found out, though, was when they started shooting these single particles, and keep in mind these are single particles, not a bunch of them, is that what happened when they shot them through there was that an interference pattern was created. So what that exposed, or what that, I guess you could say, communicated to the scientists, was that the particles couldn't be behaving as single particles. The only way they could reconcile that is if the particles were behaving as waves. So in other words, the particles had a wave-like nature, and because the waves were interfering with each other, it created an interference pattern on the screen on the back. And so in this next image, you can see a better visualization of the wave nature of particles. So they discovered that particles behave as waves sometimes. So what they did was they set up further experiments where they wanted to try to measure the particles as they came through the slits and to see them in the waves. And what they found out was that if they measured the particles, so in other words, if they set up a detector in front of those slits and said, okay, let's see if we can capture the wave going through both, the single particle, let's see if we can see how it goes through both slits. When they set up detectors, the wave pattern disappeared. So instead of one particle going through and creating a wave pattern, when they had the detectors turned on, the particle went through one slit or the other. It didn't go through as a wave. So they thought to themselves, well, that's strange. So they repeated the experiment with the detector turned off, and when they looked at the screen after some particles had gone through, the wave pattern had reappeared. So the inference that could be made from this is the only difference was that the detector was turned on. Now, it's hard to imagine how this could happen, how it could change from wave to particle, unless the particle, quote unquote, knew whether it was going to be detected or not. This is something they call the observer phenomenon, and the reason that we call it the observer phenomenon is because the detector could either be an apparatus like an electrical device, or it could be a human being. So the same thing happened. The same thing happens when a human being is observing an experiment like this through some method, which is basically what the detector is. It's allowing a human to observe it. That if you fire a single electron through this double-slit apparatus, and there's nobody watching, there's no detector, they will create interference patterns. So they're going through as waves. The minute you turn on a detector, or a human being, someone's observing it, they only go through as particles. And this has been proven several times through science experiments. So the reason this is fascinating is because, and again, there's some debate about this, just like with everything in this realm. It appears to be that the act of observing or measuring the particle going through those slits seems to determine whether or not it's a wave or whether or not it's a particle. This kind of goes into Schrodinger's cat. So maybe you've heard of Schrodinger's cat, where there's a cat in a box, and there's basically the setup is there's a cat in a box, and the cat has this there's like this drip of liquid, or there's a stuff that's based on radioactive decay of an isotope. That's a quantum process, and the cat is either alive or dead depending on what's happened with that. And because of the way particles are, where they're both a wave and a particle at the same time, the Schrodinger's cat is basically saying that the cat is both alive and dead at the same time until you open the box and make an observation. So the cat is in, they call that phase of being a wave and a particle at the same time being a superposition. And so when you hear of Schrodinger's cat experiment or thought experiment, that's what it's about. That the nature of reality at that level is basically things exist as both a particle and a wave. They're not one or the other. And it depends on whether or not it's measured or observed. Okay, so I know that was kind of a lot to get out. If you've heard of this stuff before, and maybe you're like old hat. If you haven't, it's probably really mind-bending. Like I said, I encourage you to look into it. It took me a long time to wrap my head around it. But just to make it more trippy, because that's always fun, so to push this a little bit further, and hopefully you're still with me so far, and if not, I apologize. This stuff is difficult to explain. So they wanted to do another experiment. So they said, okay, when we put the particles, when we shoot a photon or an electron through this double slit and nobody's looking, it goes through as a wave, right? When we shoot it through the double slit, but we put a detector on there, it seems to know, and it goes through one or other of those slits, right? So they wanted to try something kind of tricky. They figured, what about if we shoot the particle and we wait until after it has gone through the slits, which you would assume that if you didn't observe it, that after it had gone through the slits, it would go through as a wave, right? Because nobody looked at it. And then after it's gone through those slits, we'll turn a detector on. So they're kind of trying to fool it. They're thinking, we'll shoot it off, it'll go through the slits, and then after it's already gone through them, it should be a wave, right? Because there's no detection. Then we'll turn the detectors on, and we should be able to see the wave, like in both places, right? The thing is, when they did that experiment, and I have a little visual up here now, hopefully, when they did that experiment, what they found out was that even though they moved the detector to behind the slits, so again, like I said, the wave should have gone through as a wave first, and then once they turned it on, they should have observed the wave. What they found is that when they shot it through those slits and turned on the detector afterwards, every time they turned the detector on after, it was a particle. If they ran the same experiment and didn't turn the detector on and nobody was observing it, it was a wave. So this basically brings up the question of, not only does the particle seem to know whether to be a wave or a particle, it seems to suggest retrocausality. It seems to suggest that somehow either the particle knows before it ever even goes through there what's going to happen as far as whether it's detected, or when it's the minute the detector's turned on after it goes through, it's the retrocausality where it goes back in time and changes back to a particle. So, and again, this is where it gets really wild. This is the experiment that really blew my mind. It's called the delayed choice experiment. There's another version of it called the quantum eraser, and it's very mind-bending. If you study about it and read about it, it's just mind-bending. My mind literally hurt thinking about this stuff for many months when I was first learning about it. But the reason that I bring this stuff up is because, and the reason that it's important for people who have open minds and are spiritual, is that it basically leaves, the way I look at it is, does it prove, that we observe reality and that's what makes reality real? Not necessarily. Does it prove anything spiritual? No, it doesn't necessarily prove anything. However, it doesn't disprove it either. It leaves the door open that there's something going on that they still haven't completely explained yet, and it's very non-intuitive. You could say that the act of observation causes reality or causes particles, fundamental matter, to crystallize into form. That is not, and again, if you study it, there's these theories about something called decoherence, where they go to great lengths to make sure that there's no way you could make any spiritual inferences from it. But again, like I said, the Dalai Lama has met with quantum physicists because there's a lot of overlap. The Buddha is known for stating that all is mind. As we think, so becomes our life, basically. Well, this observer effect seems to have some kind of tie-in with that. So that's one part that I kind of wanted to communicate. And again, I encourage you to look into it. So the second part that I want to talk about, and this one's really fun, this is quantum entanglement, okay? You might have heard there's a famous saying that, well, first of all, Einstein, talking about the first part, we were talking about the Schrodinger's cat and the particle wave thing. Einstein said famously that God doesn't play dice. So in other words, things had to be determined one way or another. It couldn't be in like some random state of being a wave and a particle. So Einstein did not like quantum physics a whole lot. The other thing that Einstein said, and people have probably heard, is he referred to quantum entanglement as spooky action at a distance. So what is quantum entanglement? Quantum entanglement is basically you have two particles, and through some process, some procedure, the two particles enter a state of what they call entanglement. And basically what that means, practically speaking, is you can then take one of those particles and have it here where I am in Phoenix, and you could take the other particle and put it in a little container, put it on a space shuttle or put it on a rocket and send it out to, say, Jupiter. And the moment you make a measurement on the particle here on Earth, instantaneously, there's no time gap, the particle on Jupiter would make a correlated action, or would do like something they use as spin. So they're spin up and spin down. If the one here on Earth was spin up and I did something to manipulate it to make it spin down, the entangled particle on Jupiter would instantaneously change state the moment I did something to the particle here on Earth. You can take that even further, and you could say I have a particle here on Earth and I have an entangled particle 100 light years away. And the moment that I make an action on the particle here on Earth, that particle 100 light years away would make a correlated action at the same exact moment with no delay. Now, how can that happen? How can that happen? I mean, we're talking way beyond the speed of light here, and that's why Einstein hated it, because it breaks the speed of light, you know, the law of whatever, the law of physics, that nothing can go faster than the speed of light. They've done experiments using, most recently they used the light from quasars, and they did some experiments, some really ingenious ones that go beyond me even, but basically they have verified that using the light from quasars, that quantum entanglement works over vast, vast distances. Again, here's another thing where they like to argue, physicists and materialists, that since no information can be passed back and forth between the particles, that it doesn't really violate any laws of physics, it's not really faster than the speed of light. But there's something going on there that we can't explain yet. They can't fully explain it yet. There's a bunch of theories about different things, but to me, here's my view on it. So the universe was supposed to have started from the Big Bang, right? So at one point in time, at some point, everything in the entire universe, which this is really hard to wrap my mind around too, was compressed into an infinitely dense point. One point. So every single thing in the known universe condensed to an infinitely dense point. And then there was a huge explosion and all these particles started spreading out. Well, I don't think it's too far of a reach to consider that if everything came from one point, one particle, would not everything that sprung from it be entangled? I mean, wouldn't that little point of that one particle being apparently split, or however it got, propagated out, wouldn't everything be entangled? And if that's the case, then isn't every single particle in the universe entangled? And if that's the case, then that means everything really is connected. So when we say everything is connected, we're all connected, everybody is, I don't view it as just a spiritual truth. I think there's a real arguable point in physics, using quantum physics, that we really are all connected at a quantum level. I think all particles in the universe are connected. You can even, and again, like with everything, the materialist will argue back that you can't say that's a bridge too far, blah, blah, blah. But I don't think it can completely be argued against. In any case, whether or not it can, to me, it opens up belief. And really, that's the biggest part and the most important part for me is belief. Because when it comes to spirituality, I am, as I'm sure some people are out there, I am skeptical. I don't just believe everything people say. I don't run after every guru or every prophet or whoever who says, I know the way. I don't believe everybody's claims they make about stuff. However, I do think that there is room in science, in physics, for things that we can't explain, for unexplainable phenomena. I do think that there are things about the human mind, there are things about the universe, there are things about quantum physics that we don't know all about yet. And I think it's an injustice to human beings for scientists and materialists to say, no, you can't have any theories about that, you can't make any propositions, we know everything, we don't know this, okay, we know everything, but we don't. But you have to wait until we figure it out, until you can say what it is. You don't get to say anything. That's just not logical. That's not right. So for me personally, I have taken these quantum physics ideas, and it's helped me to get past that skeptical part of my brain that says, you can't believe in that. You really can't believe that everything's connected. And, it says, that part says to me, you know what, I can believe that, because scientifically, I can sit down and say, you know what, this makes sense to me. I'm not a quantum physicist, but at a basic level, I don't think this can be disproven. Quantum entanglement does exist. There's something going on they can't explain, so there's room for other ideas there. The wave-particle duality, it's true. There's something that happens when a particle is measured or observed that causes it to collapse from a wave into a particle. There's something going on there that's weird, and they still don't know entirely what it is. So there is room for the unknown. There is room, and again, as I mentioned before, the Buddhist, the Dalai Lama, is in talks with quantum physicists because there's a lot of correlation between Buddhism and their beliefs and quantum physics, what they're learning. There is also with what Jesus taught. Jesus said, as you do unto the least of mine, you also do to me. Well, if we're really all connected via quantum entanglement, really are doing it to, when we do something to somebody else, we really are doing it to us. We aren't consciously aware of that connection all the time, but that doesn't mean that it's not there. That would also explain things like telepathy. It would also explain things like clairaudience and all, even clairvoyancy, because of the retrocausal stuff with the delayed choice experiment, kind of points to the fact that time isn't necessarily always so strict. And so that's kind of what I guess I wanted to have this little talk be about, is quantum physics. And I apologize if this explanations weren't the best. It's very tricky, but I highly recommend you watch the movie What the Bleep Do We Know. The movie gets savaged by critics and by people who are scientists, and they say this is just all hokey and blah, blah, blah. And to be fair, there's one or two people in the movie that I think are, their beliefs are interesting and probably a little beyond where I would go. But I'm very much a person who's about, let's take in the information. I've seen something happening on UFO Twitter recently, and I don't want to get too far into it, but I think that we need to believe people and give them a chance first. And then once we reach a point where a person says or does something that maybe we don't buy in, we can take some of it and leave some of it. It doesn't have to be 100% wholesale. It doesn't have to be like, well, this movie is 100% great, or this movie 100% sucks, or everything in this book is true, or everything is false. Almost everything I've ever watched or read or encountered at all, there was a little bit that I loved, a little bit I didn't. I took the great stuff, I left the other stuff. If we get into that, painting everything as black or white, we miss out on so much possible information and so much truth. And so I encourage everybody to be a little bit more open-minded. And that doesn't mean you can't be skeptical. It doesn't mean you can't do research. It doesn't mean you can't, vet things and look for facts. But it means leave a little room for the unknown. Leave a little room for the fact that, this person is just full of it. But you know what? Maybe they say one thing, and that one thing they say is a key to an understanding that you were missing, that if you just had written that person off, you would never have gotten. So I think the more we can all remain open-minded, the more we can remain compassionate, the more we can remain welcoming while maintaining that healthy skepticism, I think the better off we'll be as people and as a community. So I guess that's my little rant on that subject. So I appreciate you taking the time to watch this with me today. I hope you'll watch What the Bleep Do We Know. It's a great Sunday afternoon movie to watch and just relax. It has a good message. There's a bunch of people in that movie that you can research after watching it. I think they give links. I'll put some links down below for you to go and do a little research. And yeah, to me it's refreshing to know that their scientists don't know everything yet. There's still stuff that happens that's weird. Like Einstein said, spooky action at a distance. I mean, the fact that Einstein said that has to, prick somebody's ear up. Like, there's something weird going on, and that makes me happy. So, appreciate your time. I wish you all the best of weeks. Peace, love, light, and many blessings to all.